Hello again, Don't Bother Kids. In this video, I'm going to try to answer your second question. How does the math show the neuron to be non-deterministic? And I hope you'll indulge me here if I go into it a little bit in depth because you're not the only ones to ask this question. Other people have wondered how this works too. So I'm going to peel into it in some detail here. Okay, math is just another language. Let me show you how equations can be used to describe physical scenarios. And let me show you what a deterministic equation looks like and what a non-deterministic equation looks like. And let me try to show how the equation which describes the neuron implies non-deterministic behavior. Okay, let's let the vertical axis here of the graph show the voltage across the membrane of this neuron. We'll measure it in millivolts. And we'll let the horizontal axis show the time in milliseconds. Okay, so probably the simplest equation, which involves both voltage and time, would be just V equals T. Voltage equals time for some time greater than or equal to 0. Notice I've given these little conditions on the end of each equation, showing at what times the equations are valid. That's actually important. Okay, so what does this look like? Well, I mean, it's just a straight line that ramps up to 45 degrees, right? At time equals 1 millisecond, the voltage is going to be 1 millivolts because V equals T. So just all the way along this line, as time increases, so does the voltage linearly. This is a deterministic equation because for every time t, it specifies there can be one and only one value for v. There's just no ambiguity here in what the solution can be. All right, let's consider another example equation now. V squared equals t squared. Now, at first glance, it seems we can just take the square root of both sides and get the same equation as we had before, v equals t. But this would actually be leaving out some important solutions. I mean, yes. For example, at time equals 1 millisecond, the voltage is equal to 1 millivolt, as shown in this figure. But if the equation is v squared equals t squared, well, 1 times 1, 1 squared equals 1, but also negative 1 squared equals 1. So at time t equals 1, v could either be 1 or minus 1. This equation also allows this as a solution to the equation, either one of them. Okay, so if this equation truly does describe a physical system, then this physical system is non-deterministic. The equation just doesn't specify. The equation is just ambiguous, really, as to what the voltage will be at any given time. It could act like this. The voltage could stay along one path, just like ramping up, or it could bounce around, kind of like this. Is just non-deterministic, right? All right, now the equation which describes the neuron is a different kind of equation. It's a differential equation. An equation like v equals t relates two numbers, v and t. When you are solving for an unknown, you're solving for a number. But there's other kinds of equations where the unknown isn't a number. The unknown is actually a function. All right. For example, okay, this is the equation which my neuron satisfied. The burden of my last couple videos on this was to show that we can make the right-hand side of the equation for the neuron here as closely approximate 2 times the square root of v as we wish. So I'm actually going to make another series of videos which more carefully explain this because there's been some questions about this as well. But at any rate, for the present, this is kind of a funny looking question. dV dt means the rate of change of voltage with respect to time. So it's basically the slope of the curve of the voltage that's there. It's not going to make much sense unless you know calculus, but I'm just going to plow ahead here and see how far I can get with this. Okay, but what we're solving for here isn't a single number. What we're solving here is for some function. V is a function of time. Okay, so what set of functions satisfy this equation? Well, it turns out that any function, it's really ambiguous. There's a whole family of functions which satisfy this equation. Vt equals t minus t0 squared. Any of these, right? T0 is basically, think of it as a knob. We can twiddle this knob. As long as t0 is greater than 0, we can twiddle this number to any number that we want to. And this function will satisfy the differential equation. All right. So again, this is going to look weird if you don't know calculus, but let me just walk through the steps here to show how this works. Okay, so dV dt equals this 2 times the square root of v. That's step 1. Step 2, what we're going to do is we're going to take 2 times the square root of this function. And if we plug in v of t equals whatever the function is, then we get 2 times t minus t naught. But also, if we differentiate this function in step 3 with respect to time, we get the same thing. So if you know calculus, it's pretty easy to verify that these family of solutions, any function of this family of functions, will satisfy this equation. All right. So what does this mean in neuron time? Well, it means that like I showed in the previous video, any time before t equals 0, the voltage is going to be, if you bring the voltage of the neuron to 0 and then let it go, it can just start ramping up anytime t less than t0. It can ramp up here, it can ramp up here, or it can ramp up here. I mean, it's just simply non-deterministic. So at any rate, hope this helps. Like I said, if you don't know calculus or differential equations, it's going to look kind of weird, but I'm afraid that's about the best I can do.